Hi. In order to understand acids and bases and pH, I thought it was important for us to get back to the basics. So I've set up here some models of water molecules. Remember during Learning Target 1 when we first learned to classify matter into either pure substances or mixtures, we said that water was a pure substance. It was a compound made of one oxygen atom that was chemically bonded to two hydrogen atoms. And that since all of the molecules in here have one oxygen to two hydrogen, they were all the same. It was a pure substance. Well, this is not exactly true. So I'm going to talk to you about what we know about water. Water dissociates. That means that some of the water molecules break apart into ions. Remember that water is always moving. This is not a static process, it's dynamic. The water molecules are moving around, they're bumping into each other, there's intermolecular forces that are happening there where they're pulling and tugging on each other and jostling around, and sometimes a hydrogen ion dissociates from the rest of the water molecule. This is just a hydrogen ion. It doesn't take its electron with it, so it's positively charged. The extra electron is left with the rest of the molecule, which is called a hydroxide ion, and that's negatively charged. This is happening throughout. Once in a while, one comes off, one hydrogen atom comes off, making a hydrogen ion and a hydroxide ion from the water molecule. Now, if you notice, when I wrote this out, I showed the arrow going in both directions. That's because this is a reversible reaction. At the same time that some molecules are breaking apart, other molecules are forming, making new water molecules. So we have some that are breaking apart, making hydroxide ions and hydrogen ions, and we have others that are forming together, making new water molecules. The more hydrogen ions that are loose, the bigger that concentration, the more likely it is that it will meet up with a hydroxide ion and form a water molecule. For that reason, there comes a point where the speed of them breaking apart is equal to the speed of them going together again. That's called equilibrium. And we know what the equilibrium of pure water is. We know what concentration hydrogen ions there would be for it to be a pure substance, for it to be water. So let's look at what concentration is. Remember back when we first learned about concentration, we said that if we have a little bit of solute in something, then it was not very concentrated. A concentration is just the measurement of how much solute there is to the solvent. If we have a lot of solute, then it is more concentrated. What we're measuring with pH is the concentration of hydrogen ions in the water. Is there a little bit or is there a lot? Is it slightly concentrated or very concentrated? pH is a measurement of the concentration. Now, the amount of water molecules that dissociate into ions in pure water is very small. It's about 1/10,000,000th of a mole in a liter. Well, how much is a mole of water? We know what a liter of water is. Here's a liter of water. A mole of water is about 18.015 grams. We know that by adding the mass of an oxygen atom and two hydrogen atoms to get the formula mass. If we say that number in grams, that is about what 1 mole of water would weigh. Well, that's just over a tablespoon. That's about that much water. So 1/1,000,000th, not of this, 1/10,000,000th of that amount of water, of 1 tablespoon of water, 1/10,000,000th of that is how much is dissociated in pure water. So the numbers that we're talking about are very small. And the way that we refer to this is using logarithms. The mathematical definition of pH is negative the logarithm of the concentration of hydrogen ions. We just talked about what hydrogen ions is. Logarithms is a mathematical term. It means a quantity representing the power to which a fixed number, the base, must be raised to produce a given number. So that's what a logarithm is. Well, we know that pH is negative the logarithm of hydrogen ions, and we know that the concentration of hydrogen ions is about 1/10,000,000th, or 1 times 10 to the 7th moles in a single liter. So the pH of pure water is going to be negative the log of 1 times 10 to the negative 7th. Well, how does that work with if we don't know logs? Y would stand for our pH, and the log at base 10 of the concentration of hydrogen ions. So 10 raised to y, 10 raised to y is going to give us the concentration of our hydrogen ions. 10 raised to y is the concentration of hydrogen ions. Looking back at this, that would mean 10 raised to 10 to the negative 7th is going to be our concentration of hydrogen ions. This negative 7 and this negative are going to end up canceling each other out, and the pH of pure water is going to be equal to 7. It's the exponent without the negative sign. It is easy to determine the pH of a liquid if the concentration of hydrogen ions is 1 times 10 to something. If this number is not 1, we have to use our calculators. But if I give you a problem and the number is 1, you're just going to look at the exponent and give me, because of this negative sign, the opposite number. So the absolute value of the exponent. So the negative 7 is going to become the 7 because of that negative sign. Acids always have a pH lower than 7. The reason is, if we have an acid, when we have all of our water molecules, there's extra. Here's hydrochloric acid. I'm putting some HCl in here. And when I put some HCl in, they dissociate, and I'm left with a lot of hydrogen ions. The chlorine ions just hang out, and we have all these hydrogen ions, these extra hydrogen ions. This is an areneous acid, and there are extra hydrogen ions, so there's a higher concentration. So how would a higher concentration of hydrogen ions result in a lower pH? Think about what this means. The pH of pure water is going to be 7 because the concentration of hydrogen ions is 1 in 10 million. If we have more hydrogen ions, if we had, say, 1 in 100 moles of of hydrogen ions, 1/100th of a mole of hydrogen ions instead of 1/10,000,000th, 1/100th in a liter, then our concentration would be 10 to the negative 2. Our pH would be 2. If we had 1/10th of a mole of hydrogen ions, then we're going to have a concentration of 10 to the negative 1. We're going to have a pH of 1. So the larger the fraction, the greater the concentration of hydrogen ions, the smaller the exponent, the closer it is to 0. So for that reason, lower pHs mean higher concentrations of hydrogen atoms. That means more acidity. The higher the concentration of hydrogen ions, the more acid a substance is, the lower the pH.